the opportunity to talk about one of my favorite topics here. So cooperative verification, what does it mean? So we have many tools for verification, and what we are missing is that the different tools cooperate with each other. So far, they work all in isolation. Okay, so when I speak about verification, I mean software verification, in particular automatic software verification. There's also interactive deductive verification where a user in cooperation with the tool tries to prove a program correct. But here, this is basically a push button technology. The input is a C program with a specification. For example, here, specification is weaved in as an assert in the program. This is given to the verification tool, and the verification tool spits out the answer true together with a witness that justifies why the verification tool thinks that the C program satisfies the specification, or it spits out false together with a witness, where the witness says, okay, here's the counter example, here's the error, a trace to a program path to the error that violates the specification. And usually this is done by over approximation. So you try to calculate the reachable states, you approximate them by calculate more of them. If you hit one of the abstract error states, then you alarm the user. So what is the status in this field? Well, 20 years ago, we had a lack of verifiers. There were only SLAM and BLAST. And currently, I just recently counted, accumulated over the last 10 years, we have 76 verification tools for software written in C and Java. So we have a lot of tools now. What can we do with these tools? First of all, as an indicator for the maturity of the research area, I would like to point out that there are several competitions actually in this research area in software verification and testing. RAS, for example, is an off-site competition. It's a competition of tools. It's open, no constraints. It's not controlled in terms of resources or what you can use. Then there's a SVComp, the one that I organize. It's an off-site competition. It's about automatic tools, and the execution is completely controlled. So resources are controlled, the time is controlled, and so on. TestComp is the pendant to SVComp, but it's not about proving specifications, but about generating test suites that satisfy certain coverage specifications. It's also offsite, automatic, and controlled. Verify This is also a competition in the area of software verification, but here the focus is on the interaction of teams with verification tools. So what is evaluated here is how quickly and how qualitatively good a team together with a tool can work out a proof of correctness for a certain software system. And this is done on the site in a classroom setting. What else can be said? So how did the number of tools grow in the last 10 years? So when the competition started in 2012, we had just 10 tools participating, but this increased every year. So in 2014, we had already more, 15, 16, and so on. And currently, actually, the most recent competition had more than 40 participants in terms of software verification tools. They all have different strengths. So there is no one verification tool that is best over all the categories. This picture is just to illustrate. These are the main categories of SVComp. It's a picture from 2019, but it didn't change a lot since then. So there's, for example, a category on reachability, there's a category on memory safety, and so on. And in each category, as you can see, there are different tools that win. VariUps wins the reachability, Symbiotic wins the memory safety, CPA checker wins the overall, and so on, right? So it's not really one tool that is good for everything. And also there are different techniques. This is too small to really read, but what I want to emphasize is there are many techniques. On the x-axis, you see techniques like CGAR, predicate abstraction, shape analysis, bit precise analysis, and so on. And on the y-axis, you see tools. And here, this illustrates that, you know, different tools use different approaches, different techniques. And this maybe explains also why they have different strengths. Right, so there is no one technique is better than the other, but the techniques are for different purposes and they are good for different categories. This is an example. I took CPA Checker because this is one of the tools that that has won several categories in the past, and is also a framework. And I want to explain that this includes a lot of features, but still, it's not possible to use this tool to beat all other tools, right? So, for example, it includes as concepts CGAR, interpolation, configurable program analysis, adjustable block encoding, conditional model checking, verification witnesses, and lots of abstract domains, for example, predicates, intervals, BDDs, octagons, explicit values, and several others. And among the approaches, so you see the keywords here from most of the very important verification approaches for software: predicate abstraction, impact, bounded model checking, K-induction, IC3, explicit state model checking, interpolation-based model checking. Right, so much of this is implemented, but yet this is not sufficient. What we need is combinations, I think, and this is the point I want to make. So we have many verifiers; they have all different strengths. Right, we have plenty of tools, and what we should focus on is cooperation between verification approaches. So the idea that I want to provoke here is, let us introduce a new level. So currently, the usual architecture of a verification tool is, you know, that the verification algorithms are at the very top level, and underneath there are, you know, there is maybe SMT solvers, and there is data structure, libraries, and so on. So what I would like to see in the future is that the verification engines also become one of the layers that we can use, just like we use libraries now. And then we can, you know, use all the engines in a way that we now use SMT solvers, SAT solvers, and so on. But what we need is clear interfaces. And this is actually what is currently missing. We have many objects that we can share, not only programs and specifications, but also conditions that describe already verified state space, or witnesses that explain the reason why a verification tool gives a certain answer, and also test suites. But there should be more, so that we can do more with the tools that we have at hand. And packaging tools as libraries and with standardized interface is successful. And if you look at SAT solving or SMT solving, then we see it, right? These implement all a common interface, a standard interface, and deliver the functionality to the user. There were also already papers describing this, that this should be done like this, but these approaches were at the time where I think the tools were not yet available as open source and as many as we have now. So we should reconsider these ideas. What are the combinations that we can have? I tried to classify the combinations into these four categories here. First, let's look. So a verification approach can be a basic one or a combination that consists of other verification approaches, right? And then the combinations, I want to partition them into two kinds. One kind of combination is working on the source code level. So it uses source code components and puts them together by extending existing components. Whereas off-the-shelf components means that I use components, but I do not change them. I use them as they are, just like libraries or, you know, binaries that I use in a way without compiling them. So the source code components, they are conceptual integrations. And this is what has been done extensively so far. The best representative is reduced product, right? We have two abstract domains. We compute a reduced product of them in order to use both abstract domains to reason about a program. But here we need to program. And the other approaches on the left-hand side, they work without changing the verification components that we use. Let me explain portfolio first. This is an idea from economics, right? You have a certain investment and you want to spread it on several different things to not lose all if your decision was not correct, right? And here in software verification, this means the investment that you have is you have a certain time and you have computing resources and you want to distribute it on various verifiers. And one approach is you start several verifiers in parallel, you divide the resources among them, and after the first delivers the result, you stop all the others and consume the result, right? But there's also a sequential combination, sequential portfolio, where you divide the time and start first one tool, then the next one, and so on, right? And if one delivers the result, then you can stop the whole sequence. Selection works completely different. Algorithm selection is also it's almost as old as portfolio. It's used for hard algorithms. So what we do is you look at the input, inspect the input, which in this case means the C program and the property, and try to find out which of the approaches has the best potential to work. And then you choose this one particular approach and start this particular tool, right? And then all the resources, all the time and all the computing resources go into this tool. So there is no division of the resources happening. And cooperative is what is the least used currently in the state of the art. So cooperative means that these off-the-shelf components are plugged together in a way such that they interchange information and try to help each other proving the program correct or finding an error. So this is what I would like to focus a bit on in the second half of this talk. But first, let me show you an idea that I use to visualize the certain components. So when we want to plug together different tools, we need types. And here I want to say that, for example, a verifier is an analyzer that takes as input a program and a specification. So these are the two input parameters and the colors are the types, right? Let's say. And the output is a result and a witness for a verifier. And a conditional verifier, for example, is a verifier that it's an analyzer that takes also as input a condition and puts out a condition. A reducer, for example, is not an analyzer, it's a transformer. It takes a program and a condition and transforms the program into a new program. Or a test extractor. So given a witness that describes an error path and a program and a specification, then a test extractor could extract a test case that shows the error trace, right? And then putting these together, then you can see, okay, if I have an analyzer, for example, that uses an output of another component, I can plug them together. Just to illustrate. Let me try to define what I mean by cooperative verification. So I would call an approach cooperative verification if there are identifiable actors that pass information in form of identifiable artifacts towards the common objective of solving a verification problem, where at least two of these actors are analyzers, right? Let me concretize this. So what is an identifiable actor? With identifiable actor, I mean any of the shelf components that I can execute to achieve some goal in verification, or binaries, even agents or even web services can be taken into account. Right, maybe this is a direction we should also consider package verification tools as web services so that they are usable without having to install them. What are identifiable artifacts? Well, we have the programs and the specifications, but we also have witnesses. We have abstract reachability graphs as proofs. We have test suites. And what are the verification problems? Usually, we say that, okay, the verification problem is given a program and a specification. Does the program satisfy the specification or not? But I think we should extend this. We should have more fine-grained verification problem. For example, a feasibility check. Given an error path, is this error path executable or not? Is it feasible, right? Or refinement, what does it mean? Refinement, so calculate a refinement for a certain situation. And then for the verification problems, we could have certain tools that solve these and exchange them, replace one by another. And now in the second half of my presentation, I would like to go through certain, I think I have 7 applications. I call it A1 is the first one. So I would like to explain what is software verification with witnesses to you. And I have several of these just to illustrate what I mean by these approaches. So witnesses are, I use this first example because witnesses are a very important interface between tools. So a verifier takes as input a program and a specification, and the output is not just the result, true or false, but it's a witness that encapsulates basically the program specification and the result. The witness explains, justifies why the result is true or false. And once we have computed the witnesses, what can we do with these witnesses? Well, we can check whether these witnesses are correct, whether the explanation of the result is believable, whether we trust it. And the tool for this is a validator. A validator is very similar to a verifier, just that it takes as input also the witness. So the validator gets as input the same program specification and result together with the witness. And it tries to reestablish the proof for the result, whether the program satisfies the specification or whether it violates the specification. And this opens a whole array of opportunities for us. For example, we can calculate verification results on untrusted resources, right? Where we don't know whether the calculation was correct or not, because we can just take the witness and see if, given the witness, we can reestablish the proof. And this would be easier than full verification, right? You all know the SAT problem. The SAT problem is NP because it's so difficult to find the solution. But once you have a satisfying assignment given, checking that this assignment is a solution for the problem is in P, right? It's much easier to solve. Well, software verification is an undecidable problem, but still, if you have given a path, then it all boils down to simulating the path to the violation of the safety property, for example. Or if you have given invariance to prove correctness, right? This is much easier than coming up with the invariance, which is the creative process. Then another approach I want to share with you is Cooperative. It's a language and a tool. So when we try to combine verification approaches, we usually need a bash script or a Python script, because we need to start one, take the results of one, pass it to the next, and so on, right? And this is a domain-specific language which is tailored to this particular task. So for example, you can instantiate a verifier from this given verification package. You can instantiate a validator from this given package and store them in the variables. So the variables here have the type actor, right? And then you can start a verify on a given program and specification. You look at the program, you look at the verdict. If they are true or false, then you do a validation of the result with the same program, same specification, and the witness, as explained before. Right. So this is just an easy way to write down how we want to combine tools. And I think this is easier to understand than a Python script or a Bash script. And at least it's typed, it's less error prone. Now, third, I would like to show that very simple combinations, even without sharing information, can give us a huge benefit. And what we did is we, in one of our projects, we gave portfolio construction. So how to construct portfolio. And of course, we used our, the Cooperative language for achieving this. So we showed how to assemble from off-the-shelf verification tools portfolios and executed them. And we showed that it is easy to, to outperform standalone verification tools with these. And now if we consider the Amazon Web Services category of, of the benchmark set that we use in the competition, we know that Amazon uses CBMC, which is a bound and mold checker, for their continuous integration checking. And they can solve, CBMC can solve almost 70 of the programs. 8 of the answers are wrong. And if we take a parallel portfolio, which is constructed from off-the-shelf verifiers that are open source, available for everybody to use, then we can, solve more than double the number of verification tasks and even have less wrong results. And important is to say that this improvement, we achieved it without changing any verification tool. We took the verification tools as they are available, right, out of the box. Another problem that we have investigated. So suppose you have a verifier A, and this verifier A, can verify some of the program paths, but not the whole program. And the verifier B can also verify some program paths, but not the whole program. But what if? So suppose these verifiers verify different program paths, and maybe the sum of them would be able to verify the whole program. The idea was conditional model checking, and so we tried to combine 2 verifiers, and the whole picture looks like this. We give a program to a conditional verifier, and the conditional verifier tells the program satisfies specification under the condition C. Here in this picture, we have illustrated, the condition C as an automaton. And the second verifier B, conditional verifier B, takes as input the program and also the condition. And the condition describes the state space of the program that the first verifier has verified already. So the verifier B can concentrate on verifying the state space that is not described by the condition C. And this basically makes it subtractive, right? So the verifier B tries to verify what A was not able to verify. And we use this condition as exchange of information here. But this idea is 10 years old already, and it's not the most cited paper I have. So the idea didn't really fly off, and we were wondering why. And well, we speculate that it is difficult to implement, a verifier that consumes these conditions, because this would involve, you not only parse the program, but you also have to parse this condition and then, construct the product in order to find out which paths are still to be verified and which are done already. So what we did is we wanted to take a verifier B and construct from it a conditional verifier B. And how to do this? Well, we want as a backend, we for sure want to use a verifier B, and this should be a general verification tool. And as input, we have a condition and the input program. And the solution is almost trivial. If I tell you, you say it's easy, but the way to go there was not that easy. So we use a reducer. What is a reducer? A reducer takes as input the input program and the condition and throws away all the passes in the program that are described by the condition. And the output basically is it's a so-called residual program that contains all the behavior that is not described by the condition. And then we dump this as a C program. So we don't have a new type of exchange object. And we can give this C program to verifier B and let verifier B run just as usual, right? Because the program does not have the verification work that B is not supposed to do. So it builds on standard input, and this is a way to reuse verifiers. So we have now, 50 or so verifiers B that we can use here. And this reducer is an own component. So basically, if somebody wants to construct a conditional model checker, he or she can use the existing components to do this. Because we have an exchange format that is an established standard. Here, the C standard. Okay, next example. CGOR, counterexample guided abstraction refinement. This is an approach that is used by many of the verification approaches. And this is implemented by many tools also. And so let me explain you how this works. So it consists of 3 steps. So it's a loop that consists of 3 steps. First, the program and the specification is given to an abstract model exploration, and this explores the program in an abstract way. If it does not find any violation of the specification, it reports the program is correct and it spits out the abstract proof of the matter. But if it finds a counterexample, then this counterexample might be due to over-approximation, right? So it might be a spurious counterexample. Therefore, we need a second component, which we call feasibility check. So this checks whether the error path is really executable in the C semantics. If it says, yes, this is feasible, then we can report a bug and we are done here. But if it is an infeasible counterexample, then we can learn from this infeasible counterexample why we encountered it and can learn facts from it that we can use as precision increment in order to make our abstract model exploration smarter. Right, so this is a refinement of our abstraction that we use. And this process goes on and on, maybe 100 times or so, and then it finally it gives us the answer. So, and I said many verification tools implement this. We have actually, I showed you that the table here at the beginning. This one, if you look at column CGOR, there are quite a few verification tools that all implement CGOR. And all these tools implement CGOR from scratch. They have their own version of it. And we were wondering, can't we decompose this algorithm such that we can have off-the-shelf components for these 3 steps here? And this is what we did. So far, we didn't have input-output interfaces, but CGOR defines them actually. So far, the instances were not exchangeable, but our goal was to change it in a modular way such that we can reuse the components. So here's what we did. Our abstract model explorer gives us output a violation witness. It's an established format. We can give this to the feasibility checker. The feasibility checker checks whether the violation witness describes a path that is realizable, executable in the program, right? And so the feasibility checker can be replaced by a validator, right? We just had a few slides earlier that if we have a witness for the result false, where the specification was violated, so we have an error path, we can use a validator to check this, right? Then if this is not feasible, then we again describe a path in a witness, put it into the witness as exchange format, have a precision refiner, and this precision refiner finds out predicates that describe why, so what went wrong with our path. And these predicates we can put into an invariant witness, right? The witnesses are an established format. So this means we have connected these three components by exchange objects that are known in the verification community already. And then we could, for example, here, we can replace this feasibility checker by, several other tools, like all the 10 validation tools that are around currently, or the precision refiner. We have experimented with different precision refiners, like one from the Ultimate tool suite, one from the CPA checker tool suite, and so on. The problem with this was it was slower than the native, homogeneous monolithic implementation of it. Why was that the case? Because we have used exchange formats that were not made for this purpose. So we have investigated a bit of time and designed new exchange formats that are better suited for this purpose. And then we had the performance back, actually. There's still a performance bottleneck because each these components need to be started in new processes. That there would be a solution for it to see these as services and have them running as a service, right, and query them. But we restarted them all the time, so it was still a bit slower. But the change from the witness format to the new proprietary format was giving us a huge performance boost. And this basically tells us that we need more formats for information exchange for verification artifacts. Another interesting approach. So there are two schools of thoughts in software verification. One is automatic verification and the other is deductive or interactive verification. And there are tools in both communities, but they are not really combined. And I would like to change this. So first of all, how is this possible? So let's look at so this is on the left-hand side, this is a program written down in, this is a C program, and it has ACSL annotated invariants. So ACSL is an annotation language that is used in pharmacy. And so here you see, you can annotate an invariant x equals y. As a user, you can insert this, and then the tool tries to prove that this is correct and tries to use this invariant to prove overall correctness that this assertion here holds, right? And if you look at the witnesses that the automated tools generate, there is the same information. Here you see the invariant is x equals y. So both syntactical representations contain the same information. So it should be possible to exchange it. And this is what we did. So there's no new verification idea here also. It's simply about transforming syntactically the objects that we deal with. So what did we do? We wanted to turn a witness validator into an interactive verifier. Right? What we did is, right, an interactive verifier is a verifier that takes as input a program with annotations and spits out the verification result. So here we take the program with the ACSL annotations and transform these ACSL invariants into our correctness witness format. And then with this correctness witness format, I can use any correctness witness validator to calculate the results, right? So from the components, just by some transformation, I can turn a witness validator into an interactive verifier. Let us try to turn an automatic verifier into an interactive verifier. What do we need here? So a verifier understands only C programs with assertions. But we can, if we have invariants given in the program, we can spit them out to a witness invariant format and read the witness invariants in and put them down in the C program as assertions. And then ask the verifier to verify the same specification, but we add to the specification that it should also check the assertions, the new assertions, right? And then we have it basically. So then the verifier takes into account the invariants that were written in the ACSL annotations. Or further, we can turn an interactive verifier into a validator. So let's take pharmacy. Pharmacy takes as input programs with annotations, and we programmed another transformer, one that takes as a witness as input and spits out a program with ACSL annotations, right? So we give the program and the witness as input, and it spits out a program, and this program is given to pharmacy with the annotations, right? And pharmacy is able to calculate a result. Or we can use an automatic verifier and turn it into a validator. This was actually already explored a few years ago. So we take the program and the witness and add the insert assertions with the invariants from the witness and give this annotated program to the verifier to produce the result. Right, so what you see is without changing verifiers and without programming new verification approaches, we can enhance what we can do with these tools. And I think we should do this more. The last example here, loop abstraction. So abstraction is key for verification. And one idea that is often used is to abstract a loop, to make it easier to analyze a loop. And so let us look at this little example program. I is initialized to 0, and while I is smaller than a certain number, we increase it, and in the end, we check that I is greater or equal to n. Right? This is clear that this, like for us as humans, it's clear that this must be the case because we know the while can only exit it if this holds. And we don't look at what happens inside the loop, right? Because this is irrelevant. And there are loop abstraction techniques that use this reasoning. So for example, if this is the control flow automaton for this little program, right? This is the loop here. It checks the condition, increases I, and so on. And it goes out of the loop if this condition holds. So it's clear that this error cannot be reached here. And a loop abstraction would be, for example, that we replace the loop here just as an havoc statement. Of course, now, if we assign I an arbitrary value, then we cannot prove anything anymore. So we need to do something. And there is, for example, havoc abstraction. So if you replace this loop or this loop here, if you replace this loop by these statements, then the program is equivalent with respect to the satisfaction of the assertion. So what does it do? We enter this body. If I is smaller than n, just as for the while loop, then we havoc I, so we forgot its previous state, and all we know that that I is not greater than n when we leave the loop, right? So whenever we hit this assert, we know that I is not smaller than n because we have left the while loop. So, and this can be used to prove the program correct without dealing with a loop. So this is one idea, and this is implemented in several tools, but the tools have implemented it in their own way inside the tool, and nobody else can use it. What we did is I want to skip one idea here and want to go straight here. So we have implemented several of these loop abstractions and decided to not use them for the benefit of CPA checker only, but we can spit out the C programs that have the loops abstracted, or even maybe better, more practical, we dump a patch that does the loop abstraction. So this way, if we have implemented a fancy loop abstraction, then everybody can use this loop abstraction, to try to take the program, make it easier, make it more abstract with the loop abstraction, and give it to an ordinary verifier to verify it. Right, so basically we have separated the concern of loop abstraction from all the other concerns of verification, so that we have component-wise solutions. And I think this is what the community of software verification has to do more, because then we can, one researcher can specialize in loop abstraction, in programming loop abstractions without dealing with, how to calculate the verification conditions and how to generate witnesses and how to, whatever is involved in a verification system, which is a very complex tool. So this was my last approach that I wanted to explain to you. In conclusion, I wanted to make the point, and I hope I got you interested a little bit in this direction. External combinations are important. So it's not only important to improve verification tools by implementing them and by extending them, but it is also important to use them externally. And for this, we need interfaces. And we have not yet defined all interface objects that we need. But then, once we have these interfaces, we can leverage combinations and cooperation as well, right? And we can do a lot. We can achieve a lot if we leverage cooperation between the tools. So this was my message, my vision for the next years of my research. And I thank you for your attention and take questions.
Thank you for another very inspiring talk. Dirk, unfortunately, you couldn't be here yesterday, but those who were can remember another talk from Christine von Rosier on more or less similar foundations, but in another subfield of verification. And I think it is really motivating to see that this field is moving towards synergy, towards cooperation, and this is always good to see. So thanks for showing this to our audience. And if you have any questions, now is the time to ask. There were no questions in the chat, nor on Discord, but hopefully people will ask in person.
I believe Matthias raised his hand.
Yes, that's true.
Yeah, thanks for the talk. It's very interesting. What are your thoughts on having, sometimes there's this joke that we think there are different solutions and we should have a standard, and then we have n+1 solutions to this. Do you think it is, have you already talked to other people about this, and what do they think on really the standardization of the exchange form? Because it's very exciting, but everybody wants their own thing in it. Do you think that will be a big challenge?
So we have one particular exchange format introduced, and this was very successful, namely the verification witnesses. So, 7 years ago, the state of the art was that the tools gave the answer true or false, and they gave, for example, the error paths describing the, how to replay the bug in proprietary formats. And this was not useful at all, because I could not read others' error formats. And actually, in the competition, we noticed that sometimes even the developers of the tools could not explain their own error path. So the definition of the standard format for verification witnesses has completely changed this. So now all the tools that participate in the competition, and these are, more than 50 a year, they support the verification witnesses, and they explain their results. And these witnesses can be used further. They are valuable information in order to, I don't know, validate or give it to a debugger. So we can also, if it is an error path, we can extract a test case from it and execute crash the program with the test vector and use a debugger to exploit and so on. So there, the standardization was very helpful and was giving a lot of power, because we now have this exchange object. And does standardization lead to an N+1 tool? Well, the original idea of standardization is exchange, so that if like we have screws, and they have a certain, different sizes, and this means that we can use different manufacturers for screws, and we can just take a screw of a certain specification and use that. And this is what I also want for verification. I want to define for a certain verification task what is the functionality. And then it doesn't matter whether I use CPA checker, ultimate automizer, or symbiotic. It gives me what it specifies, right? And this is, I think, the goal of standardization. But it is difficult to define exchange formats that all people find so useful that they implement them, right? Because the exchange formats are only useful if several implement them. SMT solving, this is a success story, right? All the SMT solvers, they implement the SMT lib standard, and this makes them so valuable, because now you can use SMT solving. You don't have the tool lock in, right? Because you can exchange the SMT solver. The same is now happening for the witness validation. Given a program specification and witness, you can use any of the witness validators to see whether the explanation makes sense. But if I go to, the example that I had here, this one, right, where I said that it works faster if I use specific exchange formats here. But then I have the problem that the other tools don't support them, right? For witnesses, I have components that work with witnesses, and I can use them readily. But with my own specification, with my own exchange format, I would need to ask the other people to support it, or we would need, a competition in feasibility checkers, and then have people participate and use those exchange formats. But I don't know if I can do, for every component that I want to foster, have an own competition. So in principle, the concern that you raised is there, yes. When you start with standards, it is always the question who supports it. And I think it needs a community And standards are done by community committees or so, right? And then there is a certain force necessary that everybody agrees to this standard and uses the standard, and then it can work. But if I just invent a standard, implement it myself, and publish it, then of course nobody else will use it, right?
Okay, yeah, thanks. I mean, then maybe there's a new category that says best collaboration use of tools. And people, you have to get out something of like a foreign tool and combine it with your tool, and then you have to understand the output of other tools.
Yeah, something like this. Yes, this would stimulate the thing. Yes, right.
If I'm not mistaken, this year there will be a category for validators, right? So this is actually happening. What you thought?
Yeah, so far validators were only used to justify scores, right? In the competition, for example, if a verifier finds a bug, then this does not mean it gets a point. The point is given only if the witness for the bug is validated successfully. Only then the verifier gets a bug. Gets a point. And now we wanted to further improve the quality of the validators, and therefore we started a track on validators this year for the first time, in the hope that this will improve the quality of the validators. And now, yes, so we have to think about Matthias's proposal of having a track or so on collaboration. Yeah, I don't know.
I think this is a nice idea. Maybe not 3 new categories every year, but slowly. Yeah. In the meantime, we had a question in the chat. Maria, do you want to read it out loud, or shall I? I saw you unmuted yourself for a second. If not, I can read it out. So the question is, it actually starts with a comment. The cooperative software verification seems to carry out the complementation between the two verifiers in order to have greater precision, and with that, to achieve the improvement of the verification by the function of each one of the verifiers. Would it be possible to use artificial intelligence in order to add these improvements to the functions of each of the verifiers or accuracy, or is AI already used for this verification? Can you also see the questions there?
Yes, I see it also, and I think I understand the question, and it's a very interesting proposal. So to the best of my knowledge, nobody has investigated the possibilities of finding cooperation or compositions of verifiers by artificial intelligence. What exists so far is there is, for example, actually several meta verifiers that use machine learning so that they do algorithm selection. So let me put up this one here. So in this category here, we have use of machine learning. So basically what they do is they train a neural network, and then once the meta verifier is started with an input and a specification, basically the pre-analysis, the classification, tells which backend verifier to use, and then this verifier is started and used, and this basically relieves the user from choosing which verifier to use, right? This is the idea behind these tools. So this is one of the things where machine learning is used, and the other where we can use machine learning, there is no verifier yet that uses it, but the approach exists in the minds, is we could use machine learning to come up with proposals for invariance. Like machine learning, right, is not able to compute invariance because it cannot prove anything, but it can suggest predicates to be used as invariance. And this is completely okay, right? Because we have validators. So we could have verifiers that come up with correctness witnesses, and these correctness witnesses are not, are not sure, are not precise. They can be wrong. But thanks to the validators, we can give these correctness witnesses to the validators, and the validators would take them in order to prove the correctness. And if it works, then the invariants were useful. So there is work on program invariant inference by machine learning, but to the best of my knowledge, none of the verification tools that participates in the competition uses this approach. But again, yeah, so these are the two applications of artificial intelligence that I am aware of, but for finding out how to combine them, this is not yet done. So thanks a lot for this idea.
Okay, so if there are no other questions, I will ask my questions. Here, can you go to the part where you showed how you output the loop simplification or the loop abstraction, and also the it was the havoc abstraction and the reducer-based construction. So I see these kind of similar in a sense that you modify the input program based on what you already computed, and then you have a simpler problem theoretically that another model checker can address. So I think this is really interesting. I have two questions. Have you tried this with the verifiers of SVComp? This is the first one. And the second one is, have you tried putting the result back in the original model checker and see if it can do anything more with that? It would be really interesting for me to see whether it can actually improve the same tool, because sometimes we see these weird phenomenon when things are not also always included.
So for the loop abstraction, we have written a paper and just published it a couple of months ago in CFM proceedings. If I forget to send you, please remind me. Otherwise, I will send you a copy. And basically, this describes a couple of experiments with that, where we showed that we can take so there is a verifier that is not able to prove this program with a loop. But if we apply our loop abstraction, then this verifier is able to prove it, right? If we give it as input the abstracted program. So this means that we can use this loop abstraction to effectively increase the precision of a verifier, right? Because we make it easier for the verifier to prove the program correct. So this is, does this answer the question? This was, right, one of your question was, did we try with tools from SVComp whether it helps? And we tried for a couple of them, not for all of them, but for some. So we found basically the paper wanted to illustrate that this can have a positive impact. We are not claiming that this proves the situation for all programs or for all tools, but we showed a couple of cases where it was helpful. And the same also for this. So we wanted to make the verification task easier for interactive tools or vice versa. So here we also showed that if we have invariants calculated with automatic tools, put the invariants into annotations, and then give the tool to Pharmacy, then Pharmacy was suddenly able to prove it correct, right? Because it had the invariant. And also the other way around. If so, there were some programs that a automatic verifier was not able to verify. If we added annotations, like from the user point of view, add annotation with an invariant, then the verifier was able to prove correctness. And I think this is like having these transformations has a lot of potential, and it's largely unused, right? And this, I mean, constructing a new verifier that outperforms others is terribly expensive and difficult, right? But if somebody has an idea for a clever transformation to make the verification task easier, right, then this maybe is much easier to implement, and we can leverage the idea.
Yes, actually, my mind is already racing through all these ideas. For example, you could split a program into several parts based on some property, and then give it to the verification tool that is good with that, and then just run them parallel, and boom, you have the result. So this is really powerful.
Yeah. So we have just an advertisement block. So there is a workshop at ETABS that is called it's the second workshop on cooperative verification. We had this workshop last time at ETABS already. It was quite successful. More than 20 people came, and we will have it again at ETABS. So if you are interested in cooperative approaches, please come to that workshop and let's discuss all these wonderful ideas. End of advertisement block.
Yeah, that's some extra advertisement. You cannot really nominate your tool for SVCom this year now, but for the next edition, people who are working on software verification tools can definitely nominate their tool in the competition. Okay, any more questions maybe? Okay, then we are quite ahead of schedule, but then we will have a longer coffee break. So the next talk will be a tutorial from Bruno Duterte about SAT SMT solving. Basically, we look under the hood in software verification and in many other fields. So see you in about 50 minutes in the same Zoom room. Thank you, Dirk. Virtual upload to the speaker, and see you in an hour.
Thank you very much. Bye-bye.
Bye, thanks.